All right. Anyone hear me?
Yep.
Good.
Here.
All right, today we got Meltdown. The reason why we're reading this paper is that security has kind of been a topic all along and comes up a lot in the design of the kernels that we talked about in the class. And as we know, the main strategy we've talked about for what it means for a kernel to provide security is isolation. In the sense that user programs can't read data from the kernel, and user programs can't read other users' data from other user programs. And the specific techniques that we've seen operating systems use in order to get isolation are things like the user supervisor mode in the hardware and the page tables in the hardware, as well as just sort of well-designed kernel software like the system calls are all defensive about how they use user-supplied pointers. But it's worth thinking about, looking at examples of how this kind of stuff goes wrong. I mean, in fact, kernels try hard to provide isolation and security, but there are problems that come up. And this paper is one of the most interesting problems that's come up with operating system security in recent times. Meltdown came out at was published at the beginning of 2018, so not too long ago. And a lot of people like me found it surprising and actually pretty disturbing attack on user kernel isolation. It really undermined faith, or sort of this very basic assumption that the page tables that the hardware supplies just get you isolation, and that's the end of the story. This attack does not support that view at all. Further, it was an example of one of a number of recent examples of what's called a microarchitectural attack, an attack that involves exploitation of hidden implementation details inside the CPU that are often not even known how CPUs work, but people guess, and they're able to make successful attacks based on correct guesses about hidden details of CPU implementation. Meltdown turns out to be fixable and seems to be pretty completely fixed. But nevertheless, it sort of set people up to fear that there might be an open-ended supply of similar microarchitectural attacks. So it's a pretty important recent event worth understanding. Let me start by just laying out the basic core of the attack. And, we'll talk about what's going on here, but this is a somewhat simplified version of the code in the paper for how the attack works. And the basic idea is that you're an attacker, and for one reason or another, you're able to run software on some computer that has some secrets that you'd like to steal. You're not allowed to directly get at the secrets, but they're in memory, maybe kernel memory or another process's memory. But you've been able to run a process, maybe because you logged into a time-sharing machine like an Athena machine, or maybe because you bought time on some hosting service. And so what the attack allows you to do is run a program in which you declare a buffer in your own memory. So this buff is just ordinary user memory that's accessible. You have the virtual address in the kernel of something that you're interested in stealing. And you issue, what I'm writing out here is sort of a mix of C and assembler, but what I mean in line 3 is that you have the address of the kernel virtual address of the data you want to steal in register 1 and R1. And on line 3, we're just imagine that this is instructions to dereference register 1 and load its results into register 2. That's the instruction that we're going to run. And then there's an instruction that just gets the low bit of register 2. So this particular version of this attack reads just a single bit, just one low bit of one memory location from the kernel, and multiply that 4096. And since it's either 0 or 1, that means that R2 will end up being 0, 4096. And then we simply read the contents of our buffer, which is a buffer in user memory, we simply read either buffer of 0 or buffer of 4096. And that's the basic attack. So one question is, why doesn't this just directly work? Like line 3, it's reading this kernel address. Can we just read addresses from the kernel? No. We all have faith that the answer can't possibly be yes. We can't possibly be able to just directly read from the kernel if we're in user space. And the machinery that we know the CPU somehow is invoking to make this not work out is that when we use a kernel virtual address, that implies a lookup in the page table. And there's permission bits in the page table. And we're just assuming that the operating system has not set the flag in the page table entries for kernel virtual addresses, has not set that flag that allows users to use those addresses. That's the PTEU flag on the RISC-V. And that therefore this instruction must fail, must cause a page fault. Right? And indeed, if we ran this code, this instruction would cause a page fault. And if we added a code after this to say print the value in register 3, we get a page fault on line 3, and we'd never get to the print statement. And we'd find we couldn't directly steal data out of the kernel. Nevertheless, this sequence turned out to be useful, as the paper shows. One thing that the paper assumes, which is no longer really true for the most part, is that the kernel is mapped into every user process's address space. That is, when user code's running, a full set of kernel PTEs is present in the page table, but they have the PTEU bit clear. So user code will get a fault if it tries to use a kernel virtual address. So all those mappings, at the time this paper was written, all those mappings were there when executing in user space. They just couldn't be used by user code, or they cause a fault if they were used by user code. And the reason why by operating system designers, mapped both kernel and user addresses when running user code is that made system calls quite a bit faster, because that meant that when a system call happened, you didn't have to switch page tables, and switching page tables usually takes time itself, and also typically causes CPU caches to be flushed, which makes subsequent code slower. So people got a boost by mapping both user and kernel mappings always in user space. But this attack relies on that habit. Okay, so I'm going to explain what's going on here that makes this code useful. But before I do that, any questions about this code fragment?
I was actually wondering if you could repeat what you just said about kernel to user mapping. It didn't really register.
Okay, let's see. You know how in XV6, when a process is executing in user space, if you look at the page table, that page table has mappings for the user addresses and for like the trampoline page and the trap frame page and nothing else. So that's how XV6 works. The page table that this paper assumes were different from that. In the time this paper was written, most operating systems would have a complete set of kernel mappings in the page table while user code was running. So all those page table entries would be there, all the kernel page table entries would be there when user code was running, but since the PTEU bit was clear on each of those page table entries, user code wouldn't actually be able to use a kernel virtual address, but the mappings were there. And the reason for that is so that when you do a system call, you didn't have to switch page tables, because you do a system call into the kernel and boom, you're using the same page table, but now you can use all those kernel PTEs because you're in supervisor mode. And that saved a bunch of time getting into and out of the kernel during system calls. So everybody used that technique. And indeed, that was almost certainly what Intel had in mind for how you should write an operating system. Okay, so that for the whole paper, that structure is assumed for the attack. Of course, getting rid of it was the most immediate solution to this problem. But at the time the paper was written, all those kernel mappings were present in user space. Other questions?
So you need to know the address that you want to get.
Yeah, that's right. It is, and so, so that's a good point. You need to know the kernel virtual address, and that's actually maybe no joke. Yeah, you might think that would make the attack harder. But first of all, a point of philosophy, in security, you just have to assume that the attacker has infinite time and patience. And that if they're after some valuable secret, they are probably willing to spend like a couple of months trying to steal that secret, or longer, right? Because it's going to be somebody's password that like protects all kinds of valuable stuff, maybe money or secret email. So that means, for example, the attacker probably has time to try every single kernel address, right? Looking for whatever precious data they're after, maybe a password. Or the attacker may have time to to look through the kernel code and look through typical compiled kernels and find addresses and maybe put print statements in their kernels to examine the structure of data in kernel memory until they understand how the kernel works well enough to be able to get an address here. Now, actually, because this game has been going on, other versions of this game, of the security game, have been going on for a long time, kernels actually defend themselves against attacks that involve guessing kernel addresses. And one of the things that was actually mentioned in this paper is this thing called kernel address space layout randomization. So modern kernels actually load the kernel at a random address in order to make it harder to guess kernel virtual addresses. And they did this long before this paper came out, because it was helpful in defeating other attacks. So this is a game, but we have to assume that the attacker, in the end, the attacker will probably win this game. Okay, so we'll just assume the attacker either knows a juicy kernel virtual address to look at, or can guess one, or is willing to exhaustively try every address. And the paper suggests that that's a plausible strategy once you have Meltdown. Okay, so what's going to happen? Well, so we're wondering, how can this code be possibly be useful to an attacker? And the answer has to do, like if the way CPUs worked was just what you read in the CPU manual, this attack clearly is nonsense. Like, it'll fault at instruction 3, and that'll be the end of it. But it turns out CPUs work in far more complex ways than is in the manual. The reason the attack works is because of some CPU implementation details. And there's actually two main things that the attack relies on. One is an implementation trick of CPUs called speculative execution, which I'll talk about first. And the other implementation trick the attack relies on is the way CPUs do caching. Okay, so first, speculative execution. And let me I have a code example for that also. And for the moment, I'm not talking about security at all. The speculative execution stuff is just a technique to improve the performance of CPUs, and sort of optimization trick that CPUs use. So imagine that we're just running this code. This is a somewhat contrived example, but it's sort of illustrates what speculative execution is all about. Supposing I have an address in say register 0, and just because of the logic of my program, the address is either valid or not valid. Maybe it contains 0 if under some circumstances, like we haven't initialized my data yet. So there's this, we'll assume there's a valid variable that's sitting in memory somewhere. And so before using the address here, this address in register 0 here on line 4, we're going to test. We're going to load valid from memory, and we're only going to use the address if valid is set to 1. And if valid is set to 0, we're just not going to use the address at all. And if valid is set to 1, then we're going to dereference the address, and, load the data it points to into register 2 and add 1 to it. And it doesn't really matter. We're going to do something with that data we loaded. In this case, add 1 to it and set register 3 equal to the data plus 1. All right, well, in a simple CPU implementation, on line 2 here, you got to load valid's a variable sitting in memory in RAM. And we have to issue some kind of, this is going to be, line 2 is going to be some sort of load instruction that reads valid out of RAM. All else being equal, if we actually have to load it from RAM, that'll take hundreds of cycles on our, say, 2 gigahertz machine. Like any load that actually has to go to RAM will take hundreds of cycles. The machine, can execute an instruction up to an instruction every cycle. So if we actually had to wait a couple of hundred cycles here, the machine would be sitting there idling for hundreds of cycles, sort of wasting its time. And because that's a significant slowdown, right? If everything went well, we'd be able to execute an instruction every cycle instead of every couple hundred cycles. All serious modern CPUs do use something called branch prediction. So this if statement is a branch. If we'd actually turned it into machine instructions, we'd see there was a branch here, and it's a conditional branch based on this test of whether register 1 is equal to 1. And what CPUs do is they use what's called branch prediction. That is, for every branch, more or less, the CPU essentially remembers a cache of information about each of the branches in your program, or at least each recently executed branch, and remembers, was the branch taken or not taken? And if the CPU doesn't have enough information to predict, so that's prediction based on the last time you executed the branch. Even if the CPU doesn't have a prediction, it may still just go ahead and execute the instructions, either that the branch takes you to or the fall-through instructions, assuming the branch wasn't taken. That is, even before the CPU knows whether this conditional is true, it'll choose one way or the other and start executing down that path, even though it might be the wrong path. It doesn't know yet. And so in this case, maybe before this load completes and before the value of valid is known, the CPU may start executing instruction 4 and do the load with whatever value is sitting in R0, which may or may not be a valid pointer. And once that load yields something, maybe even add 1 to it and set register 3 equal to that value. And then maybe a long time later, when this load at line 2 finally completes, and we know what the value of valid is, the CPU will then, it kept track of the fact that it executed lines 4 and 5 without really knowing whether that was proper. If valid is 1, then that's fine, and it just keeps going. If valid is 0, then the CPU has enough cleverness to cancel the effects of its execution of line 4 and 5 and restart execution in the proper place after the branch at line 7. And this execution of code before you know whether you really should be executing it is called speculation. And again, the point is performance. If the CPU guesses right, then it got a big head start executing these instructions and didn't have to wait for the expensive memory load. Any questions about what this means? Okay. This machinery, the hardware, the transistors in the CPU for speculation are extremely complex. There's a huge amount going on in the CPU to make this work, none of which is published, right? It's all Intel internal stuff, not in the machine manual. So surrounding Meltdown and attacks like it is a huge amount of speculation about what's probably going on inside the CPU in order to make such and such attack work or not work. Okay. Back to speculation, though. One thing that's going on is that in order to undo mispredicted speculative execution, the machine keeps shadow versions of registers, essentially. It'll assign to registers 2 and register 3, but it's assigning kind of a temporary registers. If the speculation succeeds, then those shadow registers become the real registers. If it fails, then those shadow registers are discarded. The CPU discards the shadow registers. And so these 2 assignments to R2 and R3 would just be as if they never happened. So in this code, we need to think about what happens if register 0 is a valid pointer and what happens if it's not a valid pointer, right? If we're speculatively executing line 4 and register 2 is a valid pointer, then it turns out the CPU will actually do the load and load it into at least the transient version of register 2. So we'll actually go out and try to fetch what R0 points to, and that will certainly work if the data R0 is pointed to is sitting in the cache. And I don't know if the CPU will do the load if it misses in the cache and has to load from RAM. It might. But maybe the more interesting question for us for this attack is what happens if register 0 is not a valid pointer? In that case, if we're speculatively executing here, the machine can't fault at this point because we're speculatively executing. The machine doesn't know. It may know that R0 was an invalid, that this speculatively executed instruction tried to use an invalid pointer, an invalid address, but it can't page fault because it's not sure whether this execution is a correct speculative execution or a misspeculation. And so it's only, so it can't actually raise a fault on line 4 until after the value of valid is known, and after this branch, this speculative predicted branch after the machine knows what the condition is. If the machine at line 4 sees, oh, register 0 is an invalid address, and then valid turns out to be 1, then and only then does the machine actually generate the page fault. If R0 was an invalid address and valid turns out to be 0, the machine does not generate a page fault. So the decision about whether to fault is deferred, possibly for hundreds of cycles until the value of valid is known. And the technical term for the point at which we know whether an instruction was correctly speculatively executed rather than being thrown away is called retirement. So we say an instruction is speculative and at some point it's retired, and that's when we know it's either going to be thrown away or was real and its effect should be committed to the visible state of the machine. And the rule is that an instruction can only be retired if, first of all, it's finished executing, loading memory or adding 1 to something, and every instruction before it that was executed before it has also retired. So, this line 4 can't be retired until the load of valid completes and the condition is evaluated. Only then can be retired. So if it's going to fault, it's going to fault possibly hundreds of instructions after it did the memory load or attempted to do the memory load. And as a critical detail for this attack, there's an even more, if the address in R0 is invalid and has no mapping in the page table at all, then I actually don't know what happens. If the address in R0 has a page table mapping, but there's no permission for it, that is, the PTU flag is not set, then what Intel machines actually do is load that data and assign it into the transient register 2. And where it can be used by the speculative execution of line 5. So even if R0 was an address for which we don't have permission because it's a kernel address, we'll still see its value loaded into R3 and its value +1. Sorry, we won't see it, but it will be loaded into R2 and that +1 into R3. And then when this load is retired, the machine will realize, aha, that was an invalid load because the page table entry didn't allow it. And so we're going to raise a fault and cancel the execution of the subsequent instructions and cancel the effects of this instruction, undo the modification to R2 and R3. So in this example, there's two speculations going on. One is we're speculating about where this the machine's speculating about where this branch went and just saying, oh, one way or the other, I'm just going to give that a shot speculatively. In addition, there's speculative execution after each load. We're essentially speculating about whether the machine is speculating about whether that load could complete successfully. And in the case of a load, Intel machines always just go on, if data could be provided, because it's in the cache and at least the page table entry exists, permissions or not, the machine will speculatively continue to execute. And only on retirement of the load will it actually generate the fault, and that'll cause the speculation to be canceled. All right. Any questions about this stuff?
I'm a little confused about the second speculation, which is loading R0 into R2. So does that mean that like the value of R0 is loaded into R2 and the flags are checked later?
Yes. Yes.
Okay.
So what happens, yes, that's exactly right. So what actually happens is that during the speculative phase, whatever it is that R0 points to, if there's sort of if it points to anything, if R0 points to anything, then the data at that memory location will be loaded into R2. Later, when this load is retired, and then the permissions will be checked. And if we didn't have permission to do that load, then all subsequent instructions effects will be canceled, like all these modifications to registers will be undone. And a fault will be raised with the state of the machines and registers as they were just before instruction 4.
Okay, that's interesting.
Yes.
Yes, I also have a question. Is there no possible way to restrict the CPU from checking permissions before doing a speculative load?
You mean, is there a way to cause the machine to do the check before the load?
Yes, I guess more concretely, like the only reason this is a problem, or one of the ways, is that we're just loading a page that if we can be aware that it has permissions that are gonna like be bad somehow, right? We're accessing a page that we shouldn't be able to access. Can the speculative execution be canceled given that we can read these permissions?
Yes, yes. Well, there's two answers. One is that's not the way the Intel chips CPUs actually worked. And the other answer is yes, it would have been, I believe it would have been easy for them to have done and enforced the check even for speculative loads so that even in speculation, register 2 would never have been written. So I mean, and indeed, it turns out that you may have noticed the paper mentioned that the Meltdown seems not to work on AMD CPUs, even though AMD CPUs, the instruction manual is the same as for Intel CPUs, essentially. That is, they run the same instruction set and the instructions mean the same things. The attack doesn't work on AMD CPUs. And it's widely believed that the reason is that AMD CPUs, even when speculatively executing, if you don't have permission to read this address, won't even speculatively load the value into R2. And that's why the attack didn't work on AMD CPUs. And recent Intel CPUs apparently have adopted that approach, and they actually won't speculatively load if they don't have permissions. And as far as I know, there's no particular sacrifice in performance. I think the information was all there, but just, I don't know, just say maybe a few gates, they decided only to apply it on retirement. Because they still need to do.
Yeah, that's very interesting.
Yeah. I mean, let me just warn you, there's a lot of guesswork here. And I believe what I'm saying is true, but Intel and AMD have not been very revealing about what's going on. Okay. There's some terminology here that's important. What you read in the manual for the CPU that says, oh, an add instruction takes 2 registers and adds them and puts them in a third, that stuff, that aspect of the design is called architectural. It's sort of the advertise behavior, the advertised behavior of the machine. And so the advertised behavior of the machine is that if you load from an address that you don't have permissions for, you get a page fault period and you're not allowed to load. And that's in distinction to what the machine's actually doing, which is called micro architectural. That is, actually the machine has speculative executions doing all these crazy things without telling you. And the intent of the CPU designers when they design all these complex micro-architectural optimizations is that they be transparent. That, yeah, it's doing all this stuff internally, but the results you get from programs are the same results you would get from a simpler machine that just did the straightforward thing that was in the manual. Right? They're intended to be transparent. And so, for example, at some level, what Intel is doing here is transparent. Yeah, maybe they don't check for permissions when you do the memory load, but if there was a problem on retirement, it's going to undo all these effects, and so you'll never see that memory you weren't supposed to see. So, gosh, that looks just like what the manual said. You're not allowed to load stuff you don't have permission for. So this distinction is a lot of what this attack is playing on. That the attack knows a lot about what's going on inside. Okay, other questions about speculative execution? Okay, I'm going to put that aside for a moment and talk about another piece of microarchitecture. And that's caches. And these, again, I mean, everybody knows caches are there, but they're supposed to be more or less transparent. So, and let me draw a picture of the caches I think are relevant, the cache structure that I think is most relevant to Meltdown. So, first of all, you have the core, which is the part of the machine that parses instructions and has registers and has an addition unit and a division unit and whatever, the sort of execution part of the machine. And then whenever it needs to do a load or a store, it talks to the memory system. And the memory system has a bunch of caches. So in particular, in the machines we're talking about, there's a data cache called the level 1 data cache that is maybe 64 kilobytes in size or something, not very big, but it's extremely fast. If the data you need is in the L1 cache, it'll get back to you in a couple of cycles. And the structure of the L1 cache is it has a bunch of lines, what are called lines, each of which holds probably 64 bytes of data. The lines are indexed. It's a table, really, the cache. The lines are indexed by virtual address. If a virtual address is in the cache, then the cache holds the data for that virtual address. And in addition, as it turns out, it's believed that a L1 cache entry contains a copy of the permissions taken from the page table entry that corresponds to this virtual address. So, and there's a whole, this is a table. When the core issues a load instruction, the first thing that happens is that the hardware looks in the L1 cache and see if there's a cache entry whose virtual address matches the requested the address we're trying to load from it. And if so, the machine just returns this data from the cache. And we're done very quickly. If the data is not in the L1 cache, then the next step is that we the rest of the memory system is addressed with physical addresses. So at this point, we're going to need a physical address if we missed in the L1 cache. This translation look-aside buffer is a cache of page table entries. So we're going to look up the virtual address that the program issued in the translation look-aside buffer. It may not be there, in which case now we got a lot of work to do because we've got to load the relevant page table entry from memory. But let's assume we hit in the translation look-aside buffer. And we can now get the needed physical address. Typically, there's another cache, another much bigger cache that's physically indexed with the physical address. And so we might, now that we have the physical address, we can look in this cache. And if we miss there, then we have to send the physical address after the RAM system. It takes a long time, but when we finally get data back, then we can populate the level 2 cache and populate the level 1 cache with the stuff we got back from RAM and return the data back to the core. So this is caching. By the by, the hit in L1 cache probably takes a few cycles. A hit in the L2 cache probably takes a dozen or 2 cycles. And a miss that requires you to go RAM probably takes you a couple hundred cycles. And these cycles are, less, say, half a nanosecond on a 2 gigahertz machine. So it's extremely advantageous to have caching. I mean, if you didn't have caching, you would be sacrificing a factor of a couple of hundred in performance. So these are just absolutely critical to decent performance, these caches. This cache is the L1 cache. It turns out both these caches can contain, if we're running in user space, both these caches in the operating systems Meltdown was aimed at, both of these caches can contain both user data and kernel data. The L2 cache can contain kernel data because it's physically addressed and there's just no problem. The L1 cache is a little bit trickier. It's virtually addressed. When we change page tables, the contents of the L1 cache are no longer valid because we change page tables. That means that the meaning of virtual addresses change. So you'd have to flush the L1 cache if you change page tables, although there's more complex tricks that can allow you to avoid that. But the fact that these operating systems in the days of this paper didn't change page tables when changing between user space and kernel space, because both were mapped, meant that we didn't have to flush the L1 cache, and that meant the L1 cache would have both user and kernel data in it, and that made system calls even faster. Right? If you call a system call and the system call returns, there's still going to be likely still to be useful user data in the cache because we never changed page tables or changed the meanings of these addresses. Anyway, so there's likely to be kernel data, even though you're running in user space, there's likely to be kernel data in the L1 cache. And it's these permissions, which are copied out of the TLB, copied out of page table entries, that tells the machine that, oh, even though the data is in the cache, you're not allowed to see it, and raise a page fault. So this is a good time to mention that even though the intent of microarchitectural optimizations is that they be completely transparent, that can't possibly be true, because the whole point of these microarchitectural optimizations is almost always to improve performance. And so they're guaranteed to be at least visible in terms of performance. That is, you could tell if your machine has a cache or not, because if it doesn't have a cache, it'll run a couple hundred times slower, right? In addition, you can tell whether the data you're trying to fetch, if you're capable of measuring time accurately enough and you do a load, you can tell if the load returned in a couple cycles, the data must have been cached. If the load returned after 100 times that, the data probably had to be loaded from RAM. And so the differences are profound. And if you can measure time to a few nanoseconds or even tens of nanoseconds, you can tell the difference. So in the performance level, this microarchitecture is absolutely not transparent. And all the things we talk about, like branch prediction caches or whatever, all that stuff is at least indirectly visible through timing. And so, of course, many people, even though the microarchitectural design is sort of at any detailed level secret to Intel, it's just their private business how they implement this. In fact, it's all along been of extremely intense interest to a lot of people because it affects performance a lot. So compiler writers, for example, know a lot about microarchitecture because many compiler optimizations are implicitly exploiting people's good guesses about what the machine's actually doing inside. And indeed, the CPU manufacturers publish optimization guides that reveal some of the microarchitectural tricks, but they rarely go into much detail. Certainly not enough detail to really understand sort of exactly why Meltdown works. So the microarchitecture stuff is sort of sits somewhere between supposed to be transparent and visible and hidden and sort of partially, certainly a lot of people are interested and a lot of people know all kinds of random things about it. Okay. So the reason why this cache stuff is interesting for Meltdown, first of all, any questions about caching? Okay. Let me talk then about the sort of main way that the paper uses caching. The paper talks about this technique called flush and reload. And what flush and reload is up to is that it's answering the question, did a particular piece of code use the memory at a particular address? And it's not directly a security exploit because it only works for memory that you can get at. So if you're user coding and you have some memory, that's your memory and you're allowed to use it, you can, and you call one of your own functions or, then you'll be able to tell, you can use flush and reload to tell whether the function, your function that you just executed used your memory. You can't directly use this attack, or it's not an attack. You can't use this technique to figure out if some other process used that process's private memory. Although, because processes sometimes share memory, you may still be able to do well. The right way to put it is you can only find out about memory you're allowed to access. Okay, so it's answering the question, did a particular function use this memory? So step one is we're going to flush, supposing we're interested in address X. We want to flush the cache. We want to make sure the cache doesn't contain the memory at location X. And it turns out that for our convenience, Intel supplies an instruction called CL flush. And you give it an address, and it will it will ensure that that location is not cached in any of the caches. And so that's super convenient. Even if the machine didn't provide this instruction, though, it turns out there's ways of getting rid of stuff from the cache. Like, for example, if you know the cache holds 64 kilobytes, then it's likely to be the case that if you load 64 kilobytes of random memory, just load instructions, that those will be loaded into the cache. And after you've loaded 64 kilobytes of new data into the cache, everything that used to be in it must be gone because the cache can only hold 64 kilobytes or whatever it may be. So even without this nifty instruction, you can still flush everything in the cache. Then step two is, you're interested in whether some particular piece of code uses the data at X, you just call that code, whatever it is. And it does what it does, maybe uses X, maybe doesn't. And now you want to tell if X is actually in the cache, because if it is, since you flushed it from the cache, if it's in the cache now, it must be that F caused it to be loaded, unless something else is going on. So you want to do a load, but you want to know how long the load takes. So, but we're only talking about nanoseconds, like 5 nanoseconds versus 100 nanoseconds here. How can we measure time that accurately? That's a tough assignment. However, again, the CPUs come to our aid. They, in fact, provide an instruction which gives you cycle granularity time. And it's called RDTSC. So we're just going to execute the RDTSC instruction, which tells us essentially the number of cycles that have elapsed since the machine cycles that have elapsed since the machine started. And since it's probably a 2 gigahertz machine, that means that the precision we have here is half a nanosecond, which is pretty small. And now we're going to load. We're just going to say junk equals star X. We're going to load the data at location X and get the time again. And look at the difference, right? B minus A. If B minus A is 5 or 6 or 7 or something, that means that this load hit in the cache, and that means that this function used the data. If B minus A is 150, then that means that X wasn't in the cache, and that probably means that may mean that F never used X. Now it's not quite that cut and dry, because F might have used X and then used something else that conflicted with X in the cache and caused X to be kicked out of the cache again. But for simple situations, a very large value of B minus A means F didn't use it, and a small value of B minus A means that F did use that data. So this is not an attack yet, because again, we have to be able to access this memory. So this is our memory. Any questions about flush plus reload? All right. I think that's all the preliminaries. Now let's go back to Meltdown. So this is a more full version. I showed you a sort of core of Meltdown at the beginning. This is a more complete Meltdown. And so we actually now have added the flush and reload part. Again, we're going to declare this buffer. And the idea is that depending on, we're going to be just fetching 1 bit from the kernel. And we're going to multiply that 1 bit by 4096. So we're hoping to use flush plus reload to see that either buff of 0 is in the cache or buff of 4096 is in the cache. And the reason for the large separation there is that apparently this hardware has a prefetcher in it. So if you load one thing from memory, it'll load the next couple things from memory too, the next couple cache lines. And so we can't have the 2 different cache lines that we're going to apply flush and reload to be particularly close. We need them to be far enough apart that even hardware prefetching won't cause confusion. So we put them a whole page apart. The flush part now, that we just call the CL flush instruction to make sure that the relevant parts of our buffer are not cached. Now, we're exploiting this. Line 7 is not, may or may not be necessary. What's going on here is we're exploiting this sort of we're going to be exploiting the gap in time between, we're doing this load at line 10. It's a load of a kernel address, so it's going to fault. But we're hoping to be able to execute another couple of instructions speculatively before this instruction is retired. and before it actually raises the fault and cancels these instructions, right? If this load were to be retired, say at this point, that would be too early for us, because it's going to turn out we actually need line 13 to be speculatively executed in order to complete the attack. So we want to make sure that this load isn't retired for as long as possible in order to delay the fault and to delay the speculative cancellation. Now we know instructions aren't retired until all previous instructions have retired. That's one of the rules. So at line 7, I'm imagining that we're going to launch some expensive instruction that doesn't complete for a long time. You know, maybe it loads something else that's known to have to come from RAM, so it'll take a few hundred cycles, or maybe it does a divide or a square root or something, who knows what, something that takes a long time and won't be retired for a long time, and therefore will cause this load not to be retired for a long time, giving these instructions time to execute speculatively. Okay. All right, now we're assuming again we have a virtual address in the kernel. Going to execute line 10. Line 10 won't raise a fault until it, we know it's going to raise a fault. It won't raise a fault until it retires, but we're intending, we believe we set things up so it won't retire for a while. Since it hasn't retired, and because on Intel CPUs, the data is returned even if you weren't allowed to see it. The data is returned for speculative execution, even if you didn't have permission. That means that we can speculatively execute, the machine will speculatively execute line 11 and get the low bit of kernel data now, multiplied by 4096. Line 13 is itself a load. It's another load. Using an address, basically the address of buffer plus the contents of R2, we know it's going to get canceled because we know this will fault. Right? We know the actual write to R3 will be canceled, but line 13 will cause some data from buffer to be loaded into the cache, even if it doesn't end up affecting register 3. So line 13 is going to cause something to be loaded into the cache. And in this case, depending on whether the low bit is 0 or 1, line 13 will cause the actual cache to contain either buff of 0 or buff of 4096. Then, right, and that, that, even though R2 and R3 are canceled, the change in the cache, because it's supposed to be hidden microarchitectural state, it will actually be, the cache will be changed. Finally, at some point, the fault will happen. And we need to sort of recover after the fault, but it's just a page fault, and it turns out you can, or user process can register a page fault handler and get control back after a page fault. And the paper mentions a couple of other ways of being able to continue after the fault. And so now all we have to do is figure out whether it was buff of 0 or buff of 4096 that was loaded into the cache. And now we can do the reload part of flush and reload. We, read the accurate time, load buff of 0, read the time again, load buff of 1, read the time again, and compare the two differences in time. And whichever one of these took the shorter amount of time is likely to indicate whether the low bit of the kernel data was 0 or 1. And then if we report that, repeat that, a couple of billion times, and we can scan all of kernel memory.
But in this example, if B minus A is smaller than C minus B, doesn't that mean that buff of 0 was cached?
Let's see if I got this wrong. B minus A, yeah, it means that buff of 0 was cached. Oh, yeah, you're right. Yeah. Now we're cooking. Good catch.
Oh, sorry, do you need, before we had an if, before like line 9, do we need an if now, or is it still gonna, oh, see.
No, the if was to help me illustrate the legitimate reasons for speculative execution. The ability to keep computing even though we don't know whether the branch took or not. But here, the real core of the speculation is that we don't know if this load will fault. right? And so the machine is speculatively executing past the load on the theory that it's probably, most loads don't fault, right? Or even though they may take a long time, like a load could take hundreds of cycles. So we'd love to be able to, so the machine will speculatively execute past a load, even though it doesn't, not knowing whether it's going to fault or not. And if the load did fault, it will then undo all this speculative execution. There's a speculative execution comes up anytime you have a long-running instruction that may or may not succeed. So like divide, do we know whether it's going to be divided by 0 or not? No. So instructions after a divide are also speculative.
I see.
Anyway,
Thank
the
you.
speculation, the real critical speculation starts here. Now, in fact, we tried, in order to make the attack likely to be more successful, we sort of ensured that speculation starts here, but this is the real speculation we care about. Other questions?
For this example, we've only read one bit.
Yes.
Is there some like really small, simple modification that we could make to read like a full register's size of bits?
Yeah, run this 64 times, one for each bit.
Why is it not possible to just read 64 bits at a time?
Well, 60, well, you need the buffer. The size of this buffer has to be 2 to the 2 to the number of bits you're reading times 4096 or something. So 64 bits is too big because we don't have enough memory to make a buffer that big, right? We need this, the way this is set up. Well, anyway, yeah, 64 bits is too much. You could certainly read 8 bits at a time and have this buffer size be 256 times 4096. The paper actually argues the paper observes that since most of the time is here in the flush plus reload, if you read a byte at a time, then figuring out what the bits of that byte are takes 256 flush and reloads, right? Once for each possible value. If you load a bit at a time, then each bit takes just one flush plus reload, or sort of two probes, or 2 flush plus reloads. So if you read a bit at a time, then you end up only doing 16 flush plus reloads. If you read a byte at a time, you end up doing 256 flush plus reloads. So the paper says that it's faster to do it a bit at a time than a byte at a time, which seems a little counterintuitive, but it seems to be true. Other questions?
So where would this where would this program have to be run from? Is there like any particular location on the machine? Like, does it have to be, or like where would you write it? I guess. Is there a
Where would
restriction?
you?
Like, where would this program be run from? Can it be like a user program?
Well, yeah, I mean, that depends on what kind of access you have to the machine and where the data is that you want to steal. And that, who knows, right? But one example is, supposing you're logged into an Athena dial-up machine, with a couple hundred other users, and you want to steal somebody's password, and you're patient. You can use, and let's assume that Athena is a couple of years ago, and Athena was running a version of Linux that mapped the kernel into every process's address space. Then you can use Meltdown to get out, bit by bit, or everything in the kernel, including, say, the IO buffers and the network buffers and stuff. And if somebody's typing their password, if you're lucky or patient, and somebody's typing your password and you load all of kernel memory, you're going to see that password in kernel memory, right? And because, in fact, the kernel probably maps, like xv6 maps all of physical memory that means you can probably read all physical memory, that is all of all other processes memory, using this technique on a time sharing machine. So I can see what's everybody's in text editor contents or whatever I like. Now, you have to, that's a way you could use it if you're using a time sharing machine. For other situations, it would be different.
That makes sense.
I mean, time sharing is not that pervasive anymore, but the sort of killer scenario would be some kind of cloud computing thing where you're using a cloud provider like Amazon, and which runs many customers on the same machine. And depending on the details of how they set up their virtual machine monitor or container system or whatever it may be, if you buy time from Amazon, then you may be able to peer into the memory of other customers' software running on the same Amazon machine, maybe. So I think that's the really, that's how people would actually use this probably. Actually, another time that it might be useful is your browser. When you're browsing the web, your browser actually runs a lot of code in it that is not trusted, that is supplied by the random websites that you visit. Maybe in the form of plugins, maybe in the form of JavaScript that's loaded into your browser and compiled by the browser and executed. And it is possible that this attack could be carried out by code that you run in your browser when you browse the web that you may not even know is running there, loaded from websites, and they would steal whatever stuff is sitting in your laptop. I don't know if the details of that quite work out, but.
Has anyone demonstrated an attack through either JavaScript or like WebAssembly? I
don't know. I feel certainly people were worried about WebAssembly. I don't know whether the attack was literally possible. For JavaScript, I know that maybe the sticking point was the accurate timing. That you couldn't quite get this nanosecond timing, so you couldn't quite execute flush plus reload. Now, whether somebody with a bit more cleverness could figure out a way to do it, I don't know. WebAssembly is much closer to just running machine code, and I don't know exactly how the details worked out, but boy, was it something people rapidly thought about. Okay. It turns out the attack doesn't always work, and for reasons that I don't think the authors never explained or only speculated about. And you can see, I don't know if you can see this. Well, maybe you can't see this. But if you turn to the last page of their paper, you'll see the output is actually, they mounted the attack on their own machines and extracted a bunch of data from the kernel on their own machine. And if you look closely, you'll see there's a huge, all these lines are just X, all these lines, XXs with dots. These are places where they didn't manage to extract anything, where Meltdown failed, even though they repeated it many times. And you can tell they must have been, the paper's version of this attack was retrying many, many times. Because, for example, section 6.2 that talks about performance says that in some cases, the rate at which they could extract data was only 10 bytes per second, which means they were sitting there trying again and again and again. And after thousands of times, they finally managed to get some data. That is, the flush plus reload indicated that the two cache lines had different load times. So there's something unexplained going on about why it's quite frequent for Meltdown to actually fail. I get some data. I actually got real data here, but there was also a bunch of data that they didn't get. And I don't know if people, as far as I know, people are not really sure what all the conditions are about when it succeeds and when it doesn't. The most straightforward possibility is that if the kernel data is in the L1 cache, then Meltdown succeeds. And if the kernel data is not in the L1 cache, it doesn't succeed. That's very easy to believe that could be what's going on. Because if it's not in the L1 cache, then there's a whole bunch more machinery involved in a speculative load. And it's easy to imagine that the CPU for a speculative load that's maybe not known if it's even needed, would not bother doing all the work required to load stuff from RAM. But it's not quite that simple. And you can tell it's not quite that simple because the paper says that sometimes when they retried many times, it finally worked. So there's some more complex condition, maybe a race, effectively a race inside the CPU, under which it occasionally works, even for data that's not in the cache. The end of the paper is actually also, if you didn't get that far, worth reading, because it does explain a sort of more real world, like we wanted to find out this particular thing, you know, this, like, we know there's passwords stored in our Firefox's password manager. We wanted to get them out. We wanted to steal them using Meltdown. You know, what are all the, you know, how do you find out what the address is, for example? They sort of lay out a complete attack. I mean, a complete attack done by academics, not real attackers, but nevertheless, and fill in many of the pragmatic details. The final thing I want to talk about is fixes, which we've already touched on a little bit. When this paper came out, it got a lot of attention. And there was actually another second paper by an overlapping set of people about a different attack that also used different kind of speculation inside CPUs called Spectre. So the pair of the papers came out at about the same time and was very exciting. And so people hustled. People realized that, boy, this is extremely damaging, because now what we're talking about is that, you know, isolation has been broken, right? You don't hardly, it's so basic you hardly even think about it anymore. But, you know, this is a technique for breaking page table protections, which is, you know, how we enforce isolation between user and kernel. It's like deeply fundamental attack. Or at any rate, undermines a extremely important piece of security in a very general way, right? It seems like you could read anything. And so people really, really hustled to deploy fixes for this. And the immediate fix that a lot of operating systems installed within weeks of this paper coming out, and sometimes had already installed this thing called Kaiser, and which is now called KPTI in Linux. And it's a pretty straightforward idea. The idea is just like not to put the kernel mappings in the user page table. And instead, as in XV6, switch page tables during system calls. So in user space, you just have user mappings, make a system call. There's some kind of trampoline arrangement like in XV6, and you switch page tables to a page table that has the kernel mappings in order to execute the kernel. And that causes this attack to not work because because you switch page tables, the virtual address in R1 is not only no longer valid, it's no longer meaningful because there's no translation for it. And so the CPU doesn't know what to do with it. Like, this virtual address won't be cached. It's not even in the TLB. So there's just no way for the kernel to decide what memory corresponds to this virtual address, you know, when this attack is executed in user space, because this kernel virtual address no longer means anything. It's not illegal. It's just meaningless, and so that would cause the attack not to work. The downside of this Kaiser fix is that now system calls are more expensive because switching page tables. Now, if you don't do anything, switching page tables causes the TLB to be flushed, because now all those virtual addresses in the TLB are the wrong virtual addresses. They don't correspond to this page table anymore. And it causes the L1 cache to be flushed because it's virtually addressed. And so on some machines, the switching page tables made system calls considerably slower. But recent machines actually have this trick called PCID, which you can look up, but basically makes it so you can avoid flushing these caches on a page table switch, although it still takes some time. And if you poke around in the web looking for people, there was a lot of worry at the time that this two-page table idea would be unacceptably slow. And in fact, that didn't really turn out to be a serious problem. And if you poke around, you'll see that people's guesses about typical workloads, you know, how much it impacts overall performance of typical workloads, which after all don't spend all their time entering and exiting the kernel, is like 5%. So it wasn't such a bad deal. So any questions about this Kaiser fix? So people adopted this pretty rapidly. In fact, there had been kernels that had already adopted it because it defended against some other attacks. There's also a reasonable hardware fix that I believe Intel has actually made in recent processors, and that AMD had already made. And that's basically to, because in fact, the permission, this is the structure of the cache. When an instruction loads something from the L1 cache, like this kernel data we're trying to attack, the permissions, or people believe that the permissions are sitting right there in the cache entry. And so there's no trouble with the CPU checking the permissions at that point. And indeed, AMD CPUs and perhaps modern Intel CPUs will actually do the permission check very early and won't return this data. They won't even return it to the core if the permission checks don't work out. So there's none of this speculative instructions are able to see forbidden data.
So I don't know if you know the answer to this question. It's probably just speculative, but no pun intended. But why do you think Intel would do this? Like, this seems like, okay, because to me it seems like it was a discussion. Should we check permissions on transient instructions? And they were just like, no, why bother? Well, it's just a simple check. But
why bother? Indeed, stuff's transparent, right? I mean, the user's not going to be able to see the data either way. Doing the check early, that's like some gates on a pretty critical path, right? The core to L1 data cache path is extremely performance critical, and if you can shave a few transistors off the critical path here between issuing instruction and getting the data back, that may allow you to have a slightly faster cycle time and run programs faster. And so it's got to be the case that, well, I don't know, got to be the case, but it's easy to imagine that it would have cost them a few transistors to actually enforce the permissions early. Because after all, they still need all of the stuff at retirement. It's not like doing it early would save them some work later on. They still have to defer the fault until retirement. So all that stuff's still there. Anyway, I'm just guessing that it didn't seem like it would have any advantages and would have been like a little bit of extra work. And totally, either way, completely invisible, theoretically invisible at the architectural level.
Did any kernel decide to like revert this Kaiser fix now that Intel has fixed the CPU to improve performance again?
I know it's optional on a lot of kernels. I'm not totally sure what's going on with the Intel fix. I'm fairly sure that they have this fix out there, but exactly, I don't really know what's going on.
I think the Linux kernel, you can just ask, which hardware fixes have been implemented, and Linux changes the mitigation that it enables depending on what actually the hardware tells it.
So it might actually.
So you can actually do that. Like, you can read enough info about the processor as the kernel to know what to do.
But you can run on running your laptop. There's a Linux command that is actually on it tells you exactly what fixes have been implemented, what things are mitigated in hardware. Because there's a wide range of these speculative execution attacks.
Are you saying that Linux will actually use the combined page table if the CPU?
Yes, I believe so.
Oh, cool.
Yeah, I think it was 99%. I haven't checked it recently.
Right.
I believe that's the case.
Cool. All right.
Sorry. So what were people doing? Like how did they find this? What were they trying to do?
What are they trying to do? Trying to break into computers. No. Well, who knows what they were really trying to do? I mean, the papers are written by various academics. Maybe their research is finding security problems.
I think
before the bad guys find them.
One thing that motivated them for a long time is that they wanted to break address space randomization. And they had earlier papers, with different schemes trying to break address randomization. So like one group of, one stream of researchers that were in this area had that as a background. I think the Project Zero people came from a completely different angle.
I see. Thank you.
This is people. I think Robert said this before. People have been working in this area for decades, trying to find bugs that they can exploit and understand.
So I guess maybe this is a hard question to answer, but like, how likely is it that there's another like meltdown out there? Because it seems like
extremely likely.
Okay. It's like the fundamental like thing with microarchitecture, like exposing changes. They didn't fix that.
That's right. I think part of what's going on is that the CPU manufacturers have, for decades and decades have been, adding more and more and more optimization. I mean, there's many sort of cool little tricks inside the microarchitecture for making things go faster. And, now, and people didn't worry that much, or it just wasn't on the radar that this could be like a serious security problem. And so now people are now very aware that this stuff could be a serious security problem, but we're now in a position where we're living with, 30 years of clever ideas inside the CPUs. And so indeed a bunch of, since this paper came out, and indeed before this paper came out, a bunch of this style of attacks have come to light, exploiting various different microarchitectural thingies in the CPUs. So I think this is going to be a while before this is all laid to rest.
Yeah, you look to the security conferences in the last 2 years. Basically, every conference has basically a session on like exploiting speculative execution properties and see if they can make attacks work.
And maybe a larger question is whether the situation is, well, there's 15 or 20 or 30 things that sort of have to be worked out and then we'll be done, or whether there's some much higher level approach gone wrong, that we all, this is probably way too pessimistic, but people had a lot of faith in isolation as an idea that there's like a totally reasonable thing to assume that isolation works, and we'll design stuff like cloud computing and running JavaScript in the browser and all this stuff under the assumption, which is not actually true, but was close enough, believed to be close enough to true, that isolation will just cause there not to be serious security problems. And that's actually probably still doable, but this whole bag of microarchitectural attacks has not made that story seem more convincing, that's for sure.
Just to add on to that, I'm not sure the prof's levels of expertise with like CPU design, but to what extent can CPU design be made straightforwardly without a microarchitecture while still preserving its high performance?
Oh, performance. I mean, people believe this stuff is very
nicely security too, but yeah.
Well, some of this clearly can be fixed. Like this meltdown thing, I mean, there is a fix, to actually check the permissions that probably doesn't sacrifice any performance. For some of the other attacks that have come up, it's not clear that you could fix them without sacrificing performance. I mean, some of this is very, very deep, like the fact that we're sharing, there's a lot of sharing, like in a time sharing or cloud environment, there's just a lot of sharing. And so for example, supposing there's a disk drive or a network on your cloud server, right? Gosh, you might be able to get information about the other people on that cloud server simply by watching how their traffic interferes with your traffic, disk traffic or network traffic or memory traffic or something. So there's some sort of, I don't know whether that's practical. Maybe it's not, although, for many, many things in which people said, boy, that attack just doesn't seem to be practical, it's turned out to be practical enough. And I think, and so a lot of this microarchitectural stuff maybe could be cleaned up without performance loss, or maybe can't be cleaned up without performance loss. But I think it's a much more serious problem than just we're gonna apply some fixes and they'll all go away. Like the places that have been most acute is cryptography. There's been many, many years of people looking into these kind of clever, often cache timing based ways of sensing bits out of keys and other people's cryptographic, people running, I'm running a cryptographic, an encryption on the same machine as you. Can you guess anything about my key by watching, by doing cache timing? The answer is absolutely. And it's not like a microarchitectural bug. It's, it's just a consequence of sharing often. Anyway, I don't know how all this is going to play out, but it's not straightforward.
I mean, the scariest part is when people made progress on just measuring the EM radiation from a CPU and figuring out what instructions are run and what data is in it with machine learning with like some accuracy, not 100%, not nearly, but like a scary amount of accuracy, because anything over 0 is scary.
Yeah, we all live in, there's all, well, there's a boundary between attacks that are, there's some threshold between attacks that are like possible, but gosh, just seems like that would be too expensive or awkward or painful or whatever, complex to carry out. And attacks that really could be carried out. And of course, we only should defend against the second class because the first class is often too expensive to defend against. But as the value of stuff contained in computers gets larger and attackers get more clever, get more closer access to shared environments, the kind of threshold about which attacks are feasible enough to defend against changes. All right, I'm done with the lecture, but I'm happy to take more questions if people have them.
Thank you.
Thank you.
Thanks.
Oh, I actually had a question about the cache. So the L1 cache, it's per CPU, right?
Mm-hmm.
Yes.
And the L2, is it shared for all of them?
So this picture is different for each CPU, for different models of CPU, etc. The habit today is is a little bit more complex than this. Typically, you have multiple cores, 2 or 4 or 8 or 64 or something. Each one has a L1 cache that's quite close to the CPU, but it's small, fast and small. Each core typically also has a bigger L2 cache that's, and it's sort of dedicated to that CPU. And then there's often a shared L3 cache, often but not always. And another approach is to make the summation of the L2 caches sort of convenient for all the CPUs to use, so that I have super high speed access to my L2 cache, but I can get at other people's at a slightly bigger penalty, so the effective cache size is larger. So you often see either 3-level caches or you sort of joint 2 second-level caches. And typically the L2 and L3 are physically addressed, and L1's virtual.
Sorry, so what's the point of having physically addressed? Is that because of the different processes? Oh,
it's easy. The stuff in the L1 in a virtually addressed cache, if the same data is used with different virtual addresses, you can't, the virtually addressed cache doesn't really help you find it if it was cached under a different address. Where these L2 caches, the data is independent, is usable no matter what virtual address you addressed it under.
I see.
I see. Where does the MMU sit relative to all these caches in the TLB?
Oh, it's not. It's distributed really, because the most obvious. I think in real life, the TLB, the most critical thing is the TLB, and I believe it's indexed in parallel with the L1 cache typically. Okay. Right. So if you hit in the cache, the L1 cache, great. although there may be anyway, and if you miss in the L1 cache, then now you have the physical, you were looking up in the TLB at the same time, now you have the physical address. The MMU, though, is not just a single box that sits somewhere. It's actually kind of involved.
Oh, okay. But isn't it hardware? So.
Oh, everything is here is hardware, yeah.
Ah, that's interesting.
But remember, these chips have billions of transistors on them. So yeah, maybe it's hardware, but we're talking about massively complex hardware that's designed using very sophisticated software-like design techniques so that it can do very, very complex and sophisticated things. So yeah, it's hardware, but
yeah,
it's not at all straightforward.
So do table mapping, like page table mappings, ever end up in the caches at all, or are they always just routed through the TLB? Because if you miss it in the TLB, you have to go to memory to retrieve
that
it.
Right. So certainly the L2 cache will hold from the point of view of the L2 cache, TLB misses, TLB reloads are just memory accesses. So the TLB needs to load a bunch of page table junk. It's just a memory load, and it could stuff could easily be cached in the L2.
But it has to skip the L1 because L1 has virtual addresses, which
I don't
obviously don't
think the TLB would consult the L1 for its own refill because it's virtually addressed. Yes.
Mm-hmm. And then one thing about the Spectre attack, how would you? So the thing is, like, I've heard about Meltdown and Spectre like at least a dozen times, and every time I looked it up, I would not understand it. So this is the first time I actually understand what's going on. But for Spectre, is there like how similar is it to Meltdown?
It's not.
It's not. Okay.
Or well. My understanding of the Spectre attack is by training the branch predictor that, the other code that you're trying to attack stuff from, let's suppose it's another process and you share some memory with it, right? Because it's really the same program as you, but it's some other user running the program, right? You can, the tables that the branch predictor uses are shared between different, if I run on a CPU forbidden that you run, or maybe you run on different hyperthreads of the same CPU, everybody sees the same branch, sees the same branch predictor. So I can train the branch predictor to predict branches in a certain way. And then I let you run. You're running with my branch predictor training, right? And so that means I can essentially trick your program into speculatively executing instructions of my choice, right? Now that's only speculative, so of course they'll be undone, but they will cause cache loads that to some extent I can control, because I control how you speculatively execute. And then if we share memory, I can use flush and reload to sense what cache lines your program loaded in this speculative execution that
well, so in that case, you don't need to like directly address a piece of memory. You just need to make sure that program will speculatively execute it. Like in Meltdown, we did it ourselves, but in Spectre, you just direct it there. That's kind of cool because you can just say, oh, just go and load that secret by training the branch predictor without knowing where the secret is.
Yeah.
Or like you gotta know someone. Yeah, you kind of have to know.
You need to know in great detail.
Oh yeah, sorry. Yeah, no, you have to know. But you don't have to load it yourself. Yeah.
That stuff's not secret, right? You're probably running a program that I know what program you're running,
Yep. Okay, that makes sense. Thank you.
Yeah, I was just wondering, it seems like when a research paper like this gets released, it's out there for like people with Linux and Windows and like Intel for them to try to go and scramble to patch the bug, but it's also out there for like hackers can start to like learn from the paper and be like, oh, this is a method we could use. And I'm wondering, like, as a researcher, is there a general practice of like, as we're working on the paper, we'll like sort of tip off the quote unquote good guys first so that they can get a head start on
the authors informed every the CPU manufacturers and the OS manufacturers before they publish the paper.
Yeah, there's a whole protocol, and the paper, these kind of papers won't even be accepted anymore unless you follow the protocol.
Yeah, That doesn't mean the attackers weren't already using it, right? Because
Yeah.
for all we know, the attackers discovered this 20 years ago. But
Right. Okay. Thank you.
And following the protocol is not straightforward. I think in this particular case, I think there was some Intel was not too excited about the collaboration between the Linux community and Intel was not completely smooth. I think when this happened, I think they worked out some of the kinks, but.
I think it was kind of scary because I read on Wikipedia that the Ubuntu fix was published after the paper was published, which I found scary. But yeah.
Thank you so much.
Thank you.
Thank you.
thank you. See you next week.